Okay, so in this lecture, what we want to do is we want to take the equations of the total Lagrangian formulation that we had put in the weak form in the previous lecture. We want to discretize those with some sort of a finite element discretization. Okay? But before I do that, I want to just remind you what we had developed for linear FEA. So recall, in linear FEA, right, we had the quantity m times u double dot plus k, which is the stiffness matrix, times u is equal to some reaction force vector, call it F. Let's call that equation 1. Okay? But what if, so this, as we've defined it, is really was our external forces that were applied. And so we can write this maybe as F ext. And this was effectively our internal forces, right? Let's write that as F int. And what our method basically said was that external minus internal gives us our net force, which is equal to our mass times acceleration. It's basically a statement of Newton's equations of motion. Okay? So we can rewrite equation 1 if we take this tact to get the following. We could write it more as m times u double dot is equal to F external minus F internal, which if you wanted to, we could just say this is the net force. Right? Something like that. Okay, why do I do that? Because this is the form that we're going to arrive at when we do the finite element discretization without making our assumptions of linear elastic behavior or linear behavior in general. So, right, remember when we developed these equations up here, we had fixed material properties, we had fixed geometries, and so we ended up with a nice set of equations that could be broken out in this way. We won't necessarily, when we're developing a nonlinear solution, be able to break it out as a stiffness matrix independent of u, right? It's going to be something a little bit more complex, or at least possibly more complex. Okay, so I'll just say that the form of equation 1 really can only be developed if k is independent of u. Okay, so what that means is that equation 2 is really the more general statement. So why do I do that? Is that because in this general case that we're developing, we're going to expect our solution to look like equation 2. Okay, so that's sort of my preamble to launching into this lecture proper. I just want to remind you of where we're coming from so that you aren't going, wait, why are we formulating it like this? Okay, so I wanted to show you in equation 1 and 2 sort of the linear case versus the general case, and just make sure that you're expecting the general case to come out. So that'll be the sort of the last equation that we expect to see in this lecture. So now I want to recall what we had developed in the previous lecture, where we created the weak form using the principle of virtual work. Okay, so how about recall the weak form of the total Lagrangian using the principle of virtual work. And what the principle of virtual work said was that the virtual internal work minus the virtual external work plus the virtual kinetic work is equal to 0. Let's call that equation 3. Okay, and we define those three terms. So where the virtual external work we defined as the integral from xa to xb of delta u times rho naught times a naught times b dx plus delta U times A naught times P evaluated on the boundary with tractions. Okay, so call that equation 4. We said that the internal virtual work would be equal to the integral from xa to xb of delta u comma x times a naught times p dx. Call this equation 5. And then finally, the kinetic virtual work we said was equal to the integral from xa to xb of delta u times rho naught a naught u double dot dx. Right? Call that equation 6. So as we've done before, to develop the FEA solution, we're going to assume an approximate solution. Right? And remember, we're solving for the displacement typically, so we're going to assume that our displacement approximation, u of x and t, is going to be equal to our interpolation functions, which will be functions of x transpose, times u of t, right? Where these are our nodal displacements, right? So this is all hopefully similar. Okay, so let me write these down here for you. Right, so n's are our interpolation functions, and these values of u are our nodal displacements. Okay, and I'll just put in parentheses here. Obviously, the way I'm writing it here, this is the approximation over the element. So obviously, the meshing is easy. For our 1D problem, we're going to divide the domain from xa to xb into elements. Obviously, the elements are connected at the nodes. And then we can write that for some element, so for some element in the node, okay, so for any element, call it element E, right? The nodes are going to be given as follows. X sub I, we'll put an E to remind you that they're nodal positions of the elements, and I, right, I is going to correspond to 1 up to m, however many those are, where m is the number of nodes per element. Okay, so pretty straightforward stuff. One thing I'll mention in passing here is that for any given element, okay, all interpolation functions within that element satisfy the following. Right, we can say that if I take my interpolation function, and I'm using index notation here, n sub I, so this is the ith interpolation function, and I'm interested in that interpolation function value at the jth node. That will always give me the Kronecker delta ij, right? So the only time that this quantity will give me a non-zero value is when I and j are equal, okay? Just an aside. Okay, call that equation 8. So obviously a consequence of equation 7, our approximate function, is that, remember, we had this funky term that we called the virtual displacement. And we're going to use a discretization of that as well. So I'll just say a consequence of 7 is that virtual displacements are also discretized. So what does that mean? Does that mean I can write that delta u, this is the approximate, which is going to be a function of x, is going to be equal to, approximately, right, n, which is a function of x, times transpose, times delta u sub e, okay, right, where this is the virtual displacement at the nodes of the element. Okay, we'll call that equation 9. Something I want to point out here that's actually important as we go forward. Okay, the virtual displacement at the nodes of the element are not time dependent. Okay, so, and I'm going to eventually here drop this e, because you'll know that if I have something like this inside of a vector, you'll know that means my nodal quantities. Okay. Okay, so this is kind of the crux of how we're going to get to the solution. Okay, we're going to now define the appropriate nodal forces for each virtual work term. So let me write that down, then we'll talk about it. So we would say that the virtual internal work must be equal to I'm going to say delta U, this is, nodal virtual displacements, right? Transpose times some internal force at those nodes, right? That's, by definition, has to be true, okay? Same thing here, we'll go, the external virtual work must be equal to the virtual displacement times the real external work. And then finally, we do the same thing with the kinetic virtual work. It must be equal to that virtual displacement times, we'll call this some kinetic force vector. Okay, so let's call these equation as 10, 11, and 12, right? So why do I do that? Because nodal forces are defined as the conjugate of the nodal displacements. Okay? That's important. Remember this. Okay, what does that mean? What that means, anything that's, if sometimes you'll hear things that are called, you'll hear people talk about work conjugate terms. What that means is that if you take the dot product, you get an increment in work. So what this means is that the dot product, which is what we're writing in equations 10 and 11 and 12, we're writing the dot product of the virtual displacement dotted with the nodal forces gives us an increment of virtual work in each of those terms, okay? Let me write that down. So what that means is that the inner, or the dot product of an incremental nodal displacement, right? In this case, it's just delta U, right? With a nodal force, maybe I should say with its conjugate nodal force, we'll call it F, okay, gives us an increment of work. Okay, let me say also, we didn't define what these Fint, Fxt, and Fkin were, right? All we said was that there exists some force that if we multiply the virtual displacement by, gives us a virtual work term, right? That's all we're saying. We haven't yet solved for those. That's what we want to do now, okay? So now we're going to define these nodal force terms. Okay, so let's go ahead first and let's compare equation 5 and equation 10. Okay, if we do that, I can write that the equation 10 says the virtual internal work is equal to the virtual displacement times the internal force vector, Fint. Well, that must be equal to, based on equation 5, that must be equal to the integral. And I'm not going to put xa and xb anymore because I'm doing this at the element level, okay? So can I just put, let's put x1 and x2, right? This just goes from, let's say, node, this will be the end point of the element, and this will be the starting point of the element. Okay? So going back to equation 5, this now looks like delta U partial with respect to x times a naught p dx, right? Let's call that equation 13. So if I substitute now 9 into 13. And all I'm doing is taking my approximate solution for the virtual displacement, right? I'm going to substitute that in there now. I end up with this left-hand side looks like delta U transpose times the internal force vector is equal to, now I have this integral from x1 to x2, and this looks like, this is going to look like delta U transpose times n partial with respect to x times a naught times p dx. Okay? A couple things that I need to point out here. I remember that when I wrote n transpose times delta U, that's just a dot product, right, that gives me a scalar quantity. I can equivalently write delta U transpose times n and get the same scalar quantity. I did that so that I could easily make the comparison here, okay? So if I do that, then I can look and see that, well, this delta U term is not dependent on x, right? It's just a nodal virtual displacement, so I can pull it out. Okay, so if I go ahead and just bring that down, I can write this as delta U transpose times the integral from x1 to x2 n partial with respect to x times a naught p dx, right? Let's call that equation 14. So I can just look at equation 14 and tell you what this f int term looks like, okay? So from equation 14, we have the following. Right, we have that f int is going to be equal to the integral from x1 to x2 of n comma x times a naught p dx. Call that equation 15. Okay, so there's one. Now we're going to do this again. Now let's compare 4 and 11. So if we do that, I can write the external virtual work is equal to delta U transpose times the external force vector, right? And I can go back to equation 4 and write that as the integral from x1 to x2 of delta U rho naught a naught b dx plus delta U times a naught times p evaluated on the traction boundary. Call that equation 16. Okay? So again, we substitute equation 9 in. That's our approximation for delta U. To 16. We get the following. We get this quantity delta U transpose times the external force vector is going to be equal to, and my delta U term is going to become delta U transpose times n. That delta U can come out, so I'm just going to pull it out this time. And now this becomes n times rho naught a naught b dx. I'm going to just go ahead and put a parenthesis here so it multiplies the whole thing. Then this term here becomes plus n times a naught times p evaluated at the traction boundary, right? Let's call that equation 17. So we do the exact same thing. We look at the comparator and say, aha, I know what the external force vector looks like now. So from equation 17, we can write the following. Right, that the external force vector is going to be equal to the integral from x1 to x2 times n rho naught a naught b dx plus n times a naught p evaluated on the traction boundary. Call that equation 18. Okay, so there we have it. Now we have the internal force vector and the external force vector. Now we just need to get the kinetic force vector. Okay, so finally, we're going to compare 6 and 12. Right, and we said that the virtual kinetic work is going to be equal to delta U, the virtual displacement, dotted with some kinetic force vector, and that would be from equation 6, integral from x1 to x2 of delta U times rho naught a naught U double dot dx. Call that equation 19. So now we have two substitutions we need to make. We need equation 9 to give us the approximation for delta U, but in this case we have a U by itself, so we're going to use our equation 7 approximation. Okay. So we'll say substitute 7 and 9 into 19. When we do that, we end up with delta U transpose times the kinetic force vector is going to be equal to, I'm going to pull out a delta U transpose again, right? Times the integral from x1 to x2, and then this term becomes just n times rho naught a naught, and now we have to do the U double dot term. Well, that just looks like n transpose times U double dot, right? Call that dx. Okay? Again, because this is a nodal acceleration, it's not dependent on x, so we can pull it outside. So we have then that delta U transpose times this integral term, x1 to x2 of n rho naught a naught times n transpose dx is going to be equal to U double dot, or sorry, times U double dot. Okay, let's call that equation 20. Just like before, we can look at equation 20 and now write down our kinetic force vector, right, which now looks like the integral from x1 to x2 n times n transpose times rho naught a naught dx times U double dot. Okay, let's call that 21. Okay, let's make some observations. So we observe that the integral here in 21 yields a matrix that's going to map our nodal accelerations to our nodal kinetic forces. And we're going to define that mapping as the mass matrix. Okay, we can define it as follows. We'll say the mass matrix M is going to be equal to integral from x1 to x2 of n times n transpose times rho naught a naught dx. All right, let's call that equation 22. So, and I would encourage you, go back and look at your mass matrix that we developed in the linear equations, and it looks almost exactly like this, right? So we've arrived at the same conclusions via a little bit of a different route. So what does this say? This says thus, our kinetic force vector is equal to m times U double dot. That's a pretty important conclusion. Okay? One thing to also note in all of this, how did we get to m? Well, we basically used our density, our area, and our interpolation functions, right? There's no time-dependent term, so the mass matrix is not time-dependent. So now it's pretty straightforward. Now we just need to substitute equations 10, 11, and 12 back into equation 3. And what do we get there? We get that delta U transpose times the internal force vector minus the external force vector plus the kinetic force vector is equal to 0. Let's call that equation 24. Okay, what can you say about the virtual displacement? Did we ever define that? No, we said it was acted like a weight function or a test function, right? It's arbitrary. It can be anything. So the only way equation 24 can be true for all possible virtual displacements is if that term in parenthesis is 0. Okay? So because delta U is arbitrary, equation 24 requires that the following is true, that this parenthesis term is true. So F int minus F external plus the kinetic force vector is equal to 0. Call that equation 25. So if we rearrange this, and substituting in equation 23, right, what do we end up with? M U double dot is equal to the external forces minus the internal forces, which is equal to F, which is our net force. Call that equation 26. Okay? What do you notice about equation 26? Well, it's exactly the same as equation 2. So that sort of general form that we inferred, we've now given definition to. And we did it without making any statements about the constitutive behavior of the material. Okay? So this is the finite element discretization of the total Lagrangian from the principle of virtual work, that weak form.